Good morning, class. So here are chapter 26. Today we're talking about sources of electric potential and capacitors. Why are we talking about sources of electric potential? Because charges don't just spontaneously separate. You have to do something to get that separation. So we're going to talk about a couple of different ways that can happen. First is something of a mechanical way, something like this. We call the Van de Graaff generator. And all it is a plastic belt separated by separating a metal top. And then in this control box, we have this little thing, which is a coronal discharge. It's basically something that gets hot and gives off positive ions. Take this rubber belt, run it past that coronal discharge, you put positive ions on the belt, and then because you have a larger potential on the belt than you do this sphere, you put a little pointy thing out here, and the charges will then be attracted to it and then deposit themselves on the surface of the sphere. Okay. That's one way to get a potential difference through some sort of mechanical means. Yeah. Um, you don't really see this anywhere outside of physics lecture demonstrations, but yeah, that's one way we can do it. A far more common way are batteries. So, first of all, this is a battery, and battery comes with kind of three central parts. Number one is the outside, which is, I don't know, the anode or the cathode. I think it's called the anode. Inside, you have an electrolyte, which is some sort of base fluid or gel, or it could be a solid. All it really needs to be able to do is allow for the transfer of charged particles, electrons in particular. And then you have the cathode. So in the cathode, that's where basically that's the other side of the battery. So one's positive, one's negative. The carbon is, well, kind of a positive, I think. But you have these two bits. You have the anode, which makes up kind of the battery wall, and the cathode, which goes in the center, and then you have your base kind of fluid or gel in the middle. And what happens is this gel interacts with the zinc and has an oxidation and reduction reaction, and so does this carbon rod. What that does is it builds up all kinds of electrons on the zinc. It's not just zinc, it's some sort of zinc something something. But you build up all these electrons, and what you do is then you need to give them a path. So you hook a wire and you go to the carbon, and then the electrons flow down the wire. Actually, the other way. They flow down the wire to the cathode, which is this carbon thing, which is going to have another oxidation reduction reaction with this base that you have inside. It could also be an acid. Um, car batteries are acid, but I think like flashlight batteries tend to have a base in there. Um, and then the electrons go to the carbon, and that creates your current flow, and that's how you use a battery. When we talk about the physics of a battery, we use something called the charge escalator model, which is this thing, and works like this. So we have an ion, and we talk about electricity as if positive things are moving, although it is the electrons which move kind of the majority of the time. And that just goes back to the first conventions with Benjamin Franklin. He thought positive ions were moving, so that's what we're stuck with. And it works like this. You take these positive ions, and through the work done by these chemical reactions, they're over here, you increase the potential energy of these ions till you get to the top. Okay, so when they're at the top, they're at a potential difference, delta V battery, compared to the bottom. So you could call that zero, and then this would be V battery, although we usually just talk about the difference, delta V battery. Okay, so it gains that potential due to the work done by the chemical reactions. Now, historically speaking, people thought that this worked because of something they called the electromotive force, which isn't a thing, but it still kind of shows up in that we talk about the EMF over the battery or the potential across the battery, which is the work done by the chemicals divided by one given charge. Okay. The EMF battery is going to be the potential difference when you just kind of measure across the terminals using a multimeter. Um, in an ideal battery, that EMF is the same as the battery voltage. However, that's not really the case for a real battery. That's just idealized. In a real battery, there's tends to be resistance due to this electrolyte that's inside the battery, and that reduces the potential across the terminals by a little bit. So in reality, V battery is little less than the electromotive force or the electric potential across the battery due to the chemical work. We are going to kind of ignore that difference. We might explain it a little by or give it a little model later, but we're basically going to say that if we're given a potential difference across the battery, then it's ideal and that equality holds. All right, so to recap, chemicals do work. They raise the potential energy of the charges inside the battery. That creates a potential difference, delta V battery. And there's some peculiarities in there. Batteries in series. So one of the things we're going to do is we're look at a little basic circuits, and there's kind of two ways to add circuit components. There is series, and then there is parallel. Here we have batteries in series. So what is a battery in series? It's just one on top of another. So if you imagine a path through this for an electron, it goes through one and then the other. Batteries in series just kind of keep raising the potential from one side to the other. So if you have a charge Q down here, it gets raised through delta V1, gets to here, and then it gets raised through delta V2 through the work done by the chemical reaction inside. So the potential across a series is just the sum of the potentials for those two batteries. So that's how your flashlights work. Yeah. All right. The LED flashlights don't really need a high potential. They just need a threshold potential, and then they work just fine. Okay. So batteries. We're going to be talking about batteries hooked up to basic circuits a bit later. The next thing we're going to talk about is capacitors. Now, capacitors are a useful source of storing charge and electrical energy, basically because they can be charged and discharged rapidly, whereas a battery, due to the chemical reaction, cannot be charged and discharged real rapidly. There's kind of a buffer there with the chemical reaction that happens. Now, when we talk about capacitors, there is a way to characterize them that we call a capacitance. And the capacitance is how much charge can we separate for a given potential across the capacitor delta VEC. And we characterize that with a proportionality constant, basically. And we say that the charge Q on a capacitor plate is equal to C, the capacitance, times delta VC, the potential across the capacitor. So this thing is the new thing, the capacitance, and it's how we characterize capacitors. So you can also write the capacitance is equal to Q over delta VC. And notice that that gives us units of coulombs per volt, and we call that ratio the farad. All right, and this is kind of more or less a fundamental relationship for capacitors. So let's look at something we're familiar with already, the parallel plate capacitor. So for a parallel plate capacitor, you have the electric field is equal to Q over epsilon 0 A. And we also know that the potential across a capacitor is equal to ED. So what we're going to do is put that in there and get delta VC is equal to QD over epsilon 0 A. And then I'm going to rewrite this. So I'm going to divide by delta VC and move everything to the other side to get that Q over delta VC is equal to epsilon 0 A over D, right? Which we just said was the capacitance. So the capacitance for a parallel plate capacitor is epsilon 0 A over D. Yeah, so different capacitors that have different geometries have different capacitances, but this one's kind of the most accessible. So that is the capacitance of our parallel plate capacitors. Depends on the area and the distance between them. So if we want more capacitance, we can increase the area or decrease the distance between them. All right, next, charging a capacitor. How do we charge a capacitor? Well, we make two plates to make our capacitor, separated by a small distance d. And we're going to take two wires and hook those plates up to the either terminal on our battery. The battery at a potential delta V bat is going to push charges up into the positive plate, and that's going to push positive charges away from the negative plate, creating a small current in the top and the bottom, just due to the work done by the chemicals inside the battery here. Okay, and that's going to happen until these charges can no longer push any more charges away. That is, the potential across our capacitor is equal to that of the battery. Okay. Note, this pushing of positive charges is not actually how it goes. Electrons are what move. So the electrons actually flow this way and push electrons away from here, and they go over here. That is the reality, but the convention is positive charges moving. So we talk about the charges is charging, positive charges going to the positive plate and pushing positive charges away from here, creating a current that eventually stacks up until your potentials are the same. So potential batteries equal to the capacitor. All right. Next, combinations of capacitors. So when you're building circuits, quite often you just have to deal with the fact that you don't have exactly the capacitance you want, or maybe you have to manipulate the capacitance in a number of different ways. And in order to do that, we combine capacitors together in basically one of two ways. There is either the parallel, so one capacitor hooked to the other capacitor and all the same sides are hooked together, or there is series. So the top of one capacitor goes to the bottom, and one capacitor goes to the top, one capacitor goes to the bottom of the one capacitor. Now, the way to analyze this has to do with reducing these capacitors into what we call an equivalent capacitance. Right? And the equivalent capacitance is what capacitor could we put in there in order to replace this whole network. So how do we do that? Well, let's look at parallel first. So parallel capacitors, we have two of them, VC1, VC2. The charge on VC1 is Q1, the charge on C2 is Q2. So we could replace both of those with a single capacitor who has a total charge of Q, which is equal to Q1 plus Q2. So we can calculate the equivalent capacitance by saying, okay, it's equal to Q over delta VC. And that's just Q1 plus Q2 over delta VC. So C equivalent is equal to Q1 over delta VC plus Q2 over delta VC. This is nothing more than the definition of capacitance. So C equivalent for capacitors in parallel are just the sum of the individual capacitances. And you can string that out to forever. Okay. Next. Series. So for a series, here, when we build up charge on this plate, we have positive Q here that pushes positive Q away from the opposite side, and that builds up on the next and goes and goes and goes. So when you have capacitors in series, they all have the same amount of charge, Q. Okay. Now, that leads to a potential difference across the first one, delta V1, which is equal to Q divided by the first capacitance, and a potential across the second one. Now, because of Kirchhoff's loop law, if you go around this loop here, you have delta V battery is going to be equal to delta V1 plus delta V2, because in Kirchhoff's loop law, you have delta V battery plus delta V1 plus delta V2 has got to be equal to 0. So that just tells you that delta V battery is equal to negative delta V1 plus delta V2. That is, the potential drops are Well, this is actually negative because you go from positive to negative. So that's a negative, that's a negative, that's positive. So delta V battery is equal to delta V1 plus delta V2. So our equivalent capacitor has to have a potential drop, which is equal to the sum of the potentials of those two individual capacitors. So what we say is 1 over C equivalent is equal to delta VC over Q. So you have to store the same amount of charge on your capacitor, which is equal to delta V1 plus delta V2 over Q over Q. So we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus, and you can extend that out, etc. We typically write this as this way. C equivalent is equal to 1 over C1 plus 1 over C2 plus dot, dot, dot to the negative 1, or just to be a little bit pedantic about it, 1 over C1 plus 1 over C2 plus dot, 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 dot. Okay, and we're going to use this when we start analyzing simple capacitor circuits. That'll be an exercise problem. Although if you step through the example 26.7, that's a great example of how to deal with capacitor networks. All right, so that's it for this video. If you have questions, email me or stop by Zoom. Thanks.